Okay, now let's talk about section 3.6 construction, mathematical models building functions. Okay, so in this section we will have some examples. The original problem may not directly given by the equations of functions, but we are going to use equations of functions to solve this problem. Okay. First example. Let P be the point with coordinates x and y. And this point is on the graph y equal to x squared minus 1. Okay, so this is the point on this graph. First, express the distance d from P to the origin. Express the distance d from P to the origin O as a function of x. Okay, so we're going to solve one by one. There are A, B, C, D. Let me see. There are A, B, C, D. E is about the E is a problem about computer, so about calculator. So we will skip E, just A, B, C, D parts. Let's do it one by one. Okay, distance d from point P to the origin O as a function of x. But first, what is a distance? Distance is, remember that, is the difference of x coordinate square plus the difference of y coordinate square and take square root from the Pythagorean theorem. This is distance formula. And one point is P is x, y. The other point is origin is 0, 0. So it's x squared plus y squared. Right? But here the question is to ask you express it as a function of x. Here it's a function of x and y. Now we're going to use this condition. This is a point on the graph of y equal to x squared minus 1. So the coordinates x and y satisfy the equation, which means y is x squared minus 1. So here, you're going to put x squared minus 1 here to replace y. So you get x squared minus 1 squared. Let's simplify it. This x squared minus 1 squared is x to 4 minus 2x squared and plus 1. X squared minus 2x squared. So this is your function d of x. Okay, so this is the first one. The second, what is d if x is 0? Now we do evaluation. So d of 0, or x is 0. So 0 to 4 minus 0 squared and plus 1. That's 1. And C, what is D if x is equal to 1? What is D if x is equal to 1? So we just try some evaluation. D of 1, 1 to 4 minus 1 squared and plus 1. Also 1. Here is 1 to 4 is 1, 1 squared is 1, 1 minus 1 is 0. So the first two terms cancelled. B, C, D. What is D if x is square root of 2 over 2? Because square root of 2 over 2, we are going to compute its fourth power and the squared. So let's do it. Squared is 2 over 4 is 1/2. Fourth power means that you square and square, so it is actually 1/2 squared is 1 over 4. Okay, keep this in mind. What's this? 1 minus 1/2 is 1/2. 1/2 plus 1 over 4. Square root of 3 over 4. And this number is less than that. And in fact, in the problem, the part E will use the calculator to look at the closest point to the origin, the point closest to the origin. Okay, and that is visualized by the calculator graph. And here we only do some computation. We see possibly we can only say, okay, possibly this one is is smaller. This distance is smaller than the distance at 0 and at 1. But anyway, we later in the calculus we have the more clear computation. Why at a certain point you have a smallest value? Why do you have the largest value? That is the job of a calculus. So far, even though we can read it from the graph, we don't know why. Okay, there's no powerful tools for us so far to compute to look for the smallest value and the greatest value. Okay, so the problem originally comes from the geometry, and we need to use relation and the geometric formula to construct the algebraic formula. Okay, so that's the first one. Let's see the second one. A rectangle has one corner. The rectangle has one corner in quadrant 1 on the graph of y equal to 25 minus x squared. Another at the origin third on the positive x-axis. Y-axis, and the fourth on the positive axis, on the positive x-axis. Okay, so the graph looks like this. Remember, we have the graph of the 25 minus x squared. You see that this is a parabola, and then you have this rectangle. One corner on the graph of the parabola, another corner at the origin, third corner on the positive y-axis, fourth corner on the positive x-axis. So just follow the sentences and draw this graph. Okay. Let's talk about express the area. Expresses the area A of the rectangle as a function of x. Okay. What is x? X is the x coordinate of the point on the graph of the parabola. Okay, so this is x. If this type of problem appears in the exam, the graph will be provided. Okay, so you don't have to imagine what the graph is. You will directly see it. Don't worry. So this is x. This is x. It means the projection on the x-axis is x. The projection on the y-axis is y. Okay, you project it to the y-axis, this is y, and this is x. And it's in the first quadrant, in quadrant 1, the first quadrant. So we know that the x and the y are both positive, right? X and the y are both positive. And now we want to express the area of the rectangle as a function of x. Well, what is area rectangle? One side times the other side. So the area is x times y. X is exactly this distance. Y is this distance. Okay? So this is the area. Base times height. But we want a function of x. So we have to replace y by x. Y is 25 minus x squared. It's a point on the parabola. So y, x satisfy this relation. So y is 25 minus x squared. So 25x minus x cubed. If you want, you can write it this way. Negative x cubed plus 25x. So we write the highest power first. Okay, so this is area. B. What is the domain of A? So now A is a function of x. Then what is the domain of this function? This is a geometric problem. It's not a general problem. If it's a general problem, this function has domain from negative infinity to positive infinity. But for this geometric problem, we have to study this sentence. This point, this corner is in the first quadrant on the graph. So the most left position is this position, but this position is not in the quadrant 1, in the first quadrant. It's on the y-axis. X-axis, y-axis are not in either of the quadrants. So they are the boundary. Quadrants are exactly this piece without a boundary. Okay, so the most left point is here. X is about the left, right. So the most left point is 0. The most right point is here. Okay, so we need to know the intersection, the x-intercept of y equal to 25 minus x squared. We need to know the x-intercept, at least this positive x-intercept. X-intercept, we let y be 0. X-intercept, y is 0. Y is 0. X squared is 25. We only need the positive. Let's see. Positive, x is positive, so x is 5. Okay? So we emphasize it's positive. Why? See here? The force on the positive x-axis, so x is positive. Okay, so now the most right position for x is 5. The most left position for x is 0. The domain of A is 0, 5, 0, 5. Okay, so this is the domain. The domain for some geometric problem depend on the expression of the geometric question. So you have to study it. And the natural question, technically you will see this. If I move this point very close to the left point, very close, tiny, if this way, so you will have a very, very tall but thin rectangle, then its area is small. If you make it very close to the right end point, then this is a very flat but also thin rectangle. The area is also small. So basically there is a perfect position so that the rectangle has the greatest area or the largest area. So in the calculus you can find the position so that the rectangle has the largest area. But so far you don't have that ability you don't have that tool to find it. We need the calculus, and the example tells us you use a calculator and you graphical calculator. You graph it, you estimate at which point you have the largest area. But anyway, we don't test that part. Okay, so this, we set up the equation, we determine the domain. Okay, that's a second example. Let's see the next. Example. A manufacturer of children's playpens makes a square model that can be that can be opened at one corner and attached at right angles to a wall or perhaps the side of a house. If each side is 3 feet in length, the open configuration the open configuration doubles the availability available area in which the child can play from 9 square feet to 18 square feet. Okay, from 9 square feet to 18 square feet. Now suppose that we place hinges at the outer corners to allow for a configuration like the one shown in the figure. Okay, so well, let's see. For example, you have a wall. This is a wall, and this the children's playpens. What is the children's playpens? It's basically you have a box. This box, and this box So far it's a 3 times 3, so the area is 9 square feet. And you can fix this top side, and this bottom side can be pulled. When you pull it, you see here? When you pull it, now it becomes doubled. The area is doubled. So that's what it says. Where is it? Where is it? Each side is 3 feet. I remember. Okay, the open configuration doubles the availability. So you have this, you can pull it down. You pull it down, then the area becomes bigger. So this is a pulled. That's the first one. That's the first one. So it's from 9 to 18 square feet. So this is 9. This is 9. It's like a matchbox. A matchbox. Okay, so you can pull one side to enlarge the area. And now the question is like this. So they try to modify this construction. They do something like this. Remember, this side. They make some hinges at this corner, and they do not just pull it, they pull it along a different direction. So they pull it this way. Here you can put it down, push it up, and this moment you pull it this direction. Okay, so when we pull this direction, here is still 3. This is a 3. This is a 3. This is a 3. Right? That is our current situation. This is the situation. You can make it like you can open the door. You can open the door. But when you open the door, because you actually do not open it. This part is still attached. So that when you push it, when you put it along the horizontal direction, the sides, the distance between those two vertical sides is smaller. This distance becomes smaller. Okay. So the question: build a model that express the area of the configuration as a function of the distance x between two parallel sides. Yeah. So now you see here, once you can put horizontally, these two sides, here they are vertical, but this moment these two sides are slant. But the top bottom sides are always parallel. Assume this distance is x. When you pull it, the x becomes smaller and smaller. When you push it, the x becomes bigger and bigger. Okay? So this is x. Well, let's check what is area? What is this area? I'm going to draw it here. I don't want to. I put x this point. Okay, this is a 3, 3, 3, 3. Area. This region has two parts, left part and right part. Left part is a rectangle, right part is a triangle. Right? Left part is a rectangle, right part is a triangle. The rectangle is easy to find the area. The rectangle has the area base times height, 3x. So that's not the problem. The problem is, what is the area of this triangle? This is a isosceles triangle because you have 3 and 3. Then we need base height 1/2. Where's the base? Where's the height? If we consider 3 as a base, then it's almost impossible for us to find the height. So now we are going to choose x as a base. X as a base, this is height h. This is height h. We like right triangle because in right triangle we have relation between quantities. For any other general triangles, we don't have the quantitative relation. Where is the right triangle? This is the right triangle. So let me draw it here. Okay, so the total distance between two parallel sides is x. So this is half of x because this is isosceles triangle. You draw the height from the vertex, then this point divides the base into two parts. Okay, so this is 1/2 x. The hypotenuse is 3. This side is h. Do you see this geometry? Okay, so once you get this in the right triangle, remember we like it because it has a Pythagorean theorem. So 1x/2 squared plus h squared is 3 squared. And remember the final formula should be a function of x. So we will keep x and solve for h. So h squared is 9 minus x squared over 4. H is the side of the triangle. H is positive. So h is square root of 9 minus 9 minus x squared over 4. So this is h. Okay, good. We have h, the triangle has the area 1/2 base times height. The 1/2 base times height. So the big region, big region has the area, the left plus right. So it's 3x plus 2x square root of 9 minus x squared over 4. Okay, so this is area as a function of x. See, in this problem, this is a complex and difficult problem because you have to figure out the height, draw the height in the proper position, and also you need to realize the Pythagorean theorem. Okay. The first part. The second part, find the domain. Find the domain of this area function. Well, the domain of the area function is that check here. You can, so originally it's this way. If it's this way, you cannot push it back. Push it into towards the wall from the original position. But here, the distance is 3 plus 3. So x, this is the maximum distance. And once you pull it, those two parallel sides becomes close. Sorry, here. You see it? Oh yeah, here you can see. So this is the initial position for the two moving side. And for this moment, the x has the greatest value. And once you hold this hinges and pull it to the right, and those two parallel sides will approach to each other. So x becomes smaller and smaller. When you pull this joint point to the first point, those two parallel sides will approach closer and closer and almost 0. When that happens, x becomes 0, right? Let me try to understand. Okay, so it's almost like this. So originally you have this 3 3 side. So this x is the distance between two endpoints. When you hold it, you see when you pull this point, then these 2 points, when pull this intersection point, then the distance between two endpoints becomes smaller and smaller. Eventually, it becomes 0. Right? Well, it's difficult to control those pieces by paper. And when you push it back here, you see the distance becomes bigger and bigger. And here is a smaller and smaller. So the domain is the greatest possible value is 6. 3 plus 3. This is the greatest possible value. The smallest possible value will be 0. Like this. When you pull it further, these two moving sides, they coincide. When they coincide, those two vertices will coincide and distance becomes 0. Okay? So that's the domain. And of course, after you have the domain, you can do whatever stuff, find the area, find a certain area with a certain value. So find A1 x is 5. Again, so you have 3 times 5 plus 1/2 times 5 and square root of 9 minus 5 squared over 4. 1. In the exam, once again, I want to emphasize, in the exam, you are not allowed to use calculator, even look at it, okay? So don't place a calculator around you. Hide it. And the answer can be just like this. Don't simplify. Don't simplify it. Okay? Okay, very good. So these are three examples about the construction of our functions. So we follow the definition. Sometimes we use the area formula, sometimes we use the distance formula, sometimes we use this, sometimes we use that, and all those formulas are from geometry. From geometry, you have a certain formula, you construct an algebraic function. And from the algebraic function, and you may determine the domain of the function. The domain of the function also comes from this geometric problem. You have to study the geometric problem, and this geometric problem may change. You see here, definitely something is changing so that you have the domain. Domain, you have the most left point, most right point, most top point, most bottom point, or the smallest possible position, and smallest possible value, and the greatest possible value, something like that. Okay, so do exercise, make sure you know how to set up the formulas. Make sure you know how to use the formulas, and that's it. So this is the last section covered by the first exam. Okay, so if you have a question, send me email. Okay, we'll stop here for this video, and we'll continue another video.